Okay, here's what calculus is all about. The fundamental theorem of calculus. It's going to be in a couple parts, so this is part one. It turns out if the function is continuous on a closed interval AB and you have a function that's an antiderivative of your original function on the open interval AB, if you take the definite integral of f of x dx, if you're asked to take that, it's simply the antiderivative evaluated at b minus the same antiderivative but now evaluated at a. So here are a few examples on how to use this. The first example is to calculate the area under the graph of the function f of x equals x squared that's above the x-axis. So we know our area is going to be positive, and we have the closed interval to 5. So as a definite integral, this is from 2 to 5, and our function is x squared dx, and that means I should be able to solve this by calculating the antiderivative, evaluating it at 5, and subtracting away the antiderivative evaluated at 2. One way to show this is calculate that antiderivative, so it's x cubed over 3 plus c, right? The indefinite integral of x squared dx is x cubed over 3 plus c. But this plus c is going to be in both of these terms, and you're going to subtract it away. So we don't actually need to include the plus c anymore. And now we evaluate this from 2 to 5, and what that means is substitute a 5 in, and then substitute the 2 in, and calculate this to get 117 thirds. A whole lot faster than graphing, a whole lot faster than guessing areas. It's pretty amazing that we can use an algebraic approach, pretty simple algebraic approach, to find area underneath curves. Let's take a look at another one. So in this example, we want to calculate the definite integral from negative pi over 4 to pi over 4 of secant squared x dx, and then sketch the corresponding region. So initially you should think, oh, if I were taking the definite integral of secant squared x dx, I would be talking about tan x plus c. So I want to be using tan x when I am calculating the definite integral. So the indefinite integral from negative pi over 4 to pi over 4 of secant squared x dx becomes tan x being evaluated at negative pi over 4 to pi over 4, which means I take tan x at pi over 4 and I subtract tan x. X is now negative pi over 4, and calculating that gives me 1 minus negative 1, and I get an answer of exactly 2. Now a secant squared graph looks approximately like this, and negative pi over 4 is on this side, and positive pi over 4 is on this side, and the area that I have calculated is in green, and it turns out that that area is exactly 2 units, which is pretty incredible. Each side of the y-axis would therefore be 1. Pretty neat. Are you expected to know what the secant squared, sorry, there should be an x in here, secant squared x graph looks like? No, so you can use some technology to help you actually graph or sketch that part. Let's take a look at another example. We want to evaluate what e to the 2x dx is worth when the interval is from 0.2 to 0.5, and now I need to remember how to do integration with this. It becomes 1/2 e to the 2x, getting evaluated between 0.5 and 0.2. I plug in the 0.5. I subtract away, substituting in the 0.2. I'll probably need a calculator to do this, and I get on my calculator approximately 0. And pause the video now, do the calculation, make sure you can get all the decimal places that I'm about to show, which are 6132, and I'm sure there's a bunch more decimal places. The reason I ask you to grab your calculator is not only are you going to need your calculator to be able to calculate these parts, but it turns out your calculator can do the original question by simply entering it in two different ways. So if you have your graphing calculator with you now, we're going to evaluate this next one same way we did this, and then I'm going to show you two other ways to do it using the calculator a little bit quicker. So in this one we're going to evaluate from -3 to -1, 1 over x dx, which you should know is ln x getting evaluated between -3 and -1, which is ln of -1 minus ln of -3, and that becomes, through log rules, ln of -1 over -3, which is ln of 1/3, and using your calculator, go ahead and calculate it. Pause the video if you need to. You should get -1.0986, etc. We need that on the calculator so that you can see how the calculator works to do this question in a slightly different way. So we can also do this question graphically on the calculator, which is pretty cool. If you enter in y1 as 1 over x, so that's your function, y1, and then we want to show with our window settings an interval that will include -3 to -1. So pick maybe -5 as your x min and 5 as your x max. And I'll leave it up to you to choose appropriate y min and y max. Now, before you graph it, go and calculate and use number 7 on the calculator. And this is pretty cool. Your calculator is now going to ask you for the lower limit, and in this case that's -3, and an upper limit, in this case it's 1, and then it should graph the solution for you, as well as show you a value of the integration of f of x dx. On the bottom of the screen should be that same number that we calculated before. If you can't quite see the graph, maybe zoom in on the left-hand side by altering your window settings. Maybe just go from -5 to 0 and expand your y's so that you can see. Maybe from -1 to 1 will be a little bit better. You can also do this, I'll call it numerically, on your calculator. And the way that you do that is to use the Math button and then select number 9. And number 9 says it is function integration numeric. And what it's going to ask you to fill out are some brackets. And the first thing you put in is your function. Then you say what variable you are using, and you put your lower and your upper limits. So in this case, we're going to have the notation 1 over x. The variable is x. The lower limit is -3, and the upper limit is -1, and that should also give us that same value. Go ahead and do it so that you know where those keystrokes are and how to enter it in on the calculator. These calculators are pretty incredible when you get to know all the inner features of them. They can really help you calculate things much faster than by evaluating everything by hand. If you have a multiple choice question, doing it graphically or numerically is obviously an advantage. If you have to show your work, then the evaluation method I show you at the top with the antiderivative of b minus the antiderivative of a and showing those steps is the way to go. Come to class, be prepared to tackle some questions, and we'll see you then.